a lot of the stuff we have been going over in class. And so in your various classes. So I mean you can see like the anatomy and the structures of the eye, the refractive errors. We'll be going over a little bit of that today. This is all from theory, your electromagnetic spectrum, refraction, index of refraction, the speed of light, using the speed of light formula, speed of light over the material gives you that refractive index, or you can switch those around. Prism lenses, lens power and formulas. That's kind of very much in line with what you're learning in your lab class. The nominal power formula, front plus back equals power. That's distracting. Lens forms, the sphere, still axis, aspheric lens design. We started touching on a little bit of that in that last lens curve assignment in lab that you're working on. Flat transposition and optical crosses, prism. We'll be going over that a little bit today and kind of helping you try to figure out that base direction and whether whether the OC is misplaced or whether the eye is looking somewhere else. You just have to find a good system for sketching those out. So we'll talk about that as well too. Um, yeah, and so it kind of goes through all these compounding and canceling prism, prism power, and meridians, the oblique meridian formula. Then it goes over some stuff about lens materials, AR coatings, photochromic, polarization tints, and then your progressive and multifocals and slab off as well. And then written prescription, we got stuff in here for frames and some basic lensometer with lens clock verification and ANSI. So I read through this because this is all my highlighting, and I made some points at times, but this is all like this is all pretty much what you're going to see on the exam 100%. Knowing how to label all of these and how, the points on the eye and knowing a little bit about them. So we'll talk too a little bit about that. Like, for example, the ciliary body and knowing that ciliary body is where the aqueous comes from, because remember this all in here in the eye itself has that vitreous humor. Is that large enough? In the eye we have this vitreous humor, and that's what helps give it the that shape, a little bit more jelly-like substance, and that doesn't kind of reproduce or anything like that. So it doesn't reproduce or exit the eye in any way, but the aqueous that is in this front part of the eye, that is replaced and is actually created by the ciliary body, which is right in this area, right around behind the iris, if you will, kind of. And then knowing the little parts that the zonules, those little strings or whatever that are holding the actual crystalline lens in there. Um, yeah, and knowing that it comes out through here, you should be familiar with the canal of Schlemm, which is kind of right on the limbal margin here. And that's how that aqueous comes through this posterior chamber, which is behind the retina, washes the front of the lens, exits out the pupil, swirls around in this anterior chamber, so in the front, swirls around in there, provides, back surface nutrients to the backside of the cornea, and exits through the canal of Schlemm out into the tear film on the exterior part of the eye. So um, that path of that aqueous is important to know as well. Then you got your different parts, your sclera being that white part that's outside of the eye. That's the white part that we see, and that's that kind of fibrous. helping also to give structure and stability to the eye. Then that next layer is the choroid, and that's where you have all the veins, kind of all your blood supply. You can see them through the retina right here coming in. So that's the choroid, and then the next layer moving in is the retina, and the retina is the light sensitive layer of the eye. And then we have the macula here at the very center area. This is like the main point where when light comes in, it focuses on this macula area. You probably have heard of macular degeneration. That means like a loss of central vision because the macula is, for whatever reason, starting to separate or um, come away from or is damaged in some way. So, but the macula is the whole area there. The very, very center is that fovea. And the fovea centralis, that's how I always kept them straight, knowing that, was it the fovea is the whole area and the macula is the very center, and the macula is the whole area and the fovea centralis is the very center point. Of course, you've got your optic nerve. That's the, kind of the supplier and where all that information that's gathered by the retina is sent back to the brain where vision actually happens. And right here, where this connects into the eye, where that optic nerve connects into the eye, we have a blind spot, right? Everybody is familiar with that. We got a blind spot right there, but the brain actually makes up for it, and just kind of fixes it and blends it in. There are certain little things you can do on. Is somebody sitting in? Hold on, sorry, y'all. I don't know if somebody tried to come in. Waiting in the lobby, Greg. Here we go. Okay. Where was I? Yeah, so there's certain little websites that you can go on to, and they'll show you like a way for you to actually kind of see that blind spot. So that's just kind of neat. But anyway, so that's the one place that we don't have vision. There's no rods or cones that are active. It's kind of the central power place where everything goes back to the brain. I covered all those. You got your iris right in here. That's the colored part of the eye. And then the pupil is kind of the absence. It's an absence of a part, really, because it's just the hole where the light can go in. But the iris is actually the part that I don't think I can zoom in anymore, but the iris is actually the part that controls that light. It has that kind of sphincter kind of thing. If Greg's listening, he giggled. Um, see, and then oh yeah, there was the canal of Schlimm.
I
This
sorry.
you giggled. Okay. Let's see, and then we've got the cornea, of course, right here. That's the clear part of the eye. That's about the thickness of the peeling of a grape. So when you think about them doing the uh, doing those surgeries on the cornea and reshaping the cornea, if you could just imagine how thin these layers that they're working with to reshape. So the other thing is knowing this breakdown of the cornea, you're almost guaranteed to get this question in some shape or form. And you see this pink, you got your epithelium on the outside, then Bowman's, and that's that membrane that kind of separates the epithelium from the stroma. The stroma being the thickest part, that's where you got, all the kind of the nutrients and you've got these little fibers in there that need to stay in the same kind of alignment so that it continues to be clear. And when they get out of alignment because either too much water or not enough water, they get out of alignment, and that's what causes edema and kind of blurry vision, which is pretty common. Um, let's see, and then you've got Descemet's membrane, which is the one that kind of separates the stroma from the endothelium, which is the inner layer. And you can see the thickness here. Remembering that the epithelium is 5 to 6 layers thick is really important because the endothelium, the one on the inside, is not. It is only like one layer, one cell layer thick. But if you think about the reason we need extra layer out here is because that's the one on the outside of our body. So if we get a scratch, it has a way to kind of regenerate and repair itself, and it gives it a little bit more protection than just a single cell layer. So that's kind of, if you ever got one that was literally just a box and it just had the different layers laid out, you would be able to determine which one was the epithelium and which one's the endothelium, or the outside versus the inside layer based off the cell thickness. So just keep in mind that it's on the outside of the body, so more layers is important. But that kind of all talks about that in here. And you guys had come up with, I think somebody shared it, the to keeping these straight, whether Bowman's, was it epithelium Bowman stroma, or was it epithelium Descemet's stroma? They said that the ABCs, that B comes before D in your ABC. So Bowman's on the outside, Descemet's on the inside. I just thought that was cute that he had that same little um, memory there, memory thing. Um, let's see. So looking at this diagram, could you label those right there? What's this part right here, this inside?
Stroma, right?
Yeah, and then the outside layer, this thicker one.
Epithelium.
Mm-hmm. The inside, this single layer.
Endothelium.
All right. And what's the limiting membrane between the epithelium and the stroma?
Bowman's first.
Bowman's, right? Bowman's. And then we got the stroma to the epithelium. What's the membrane that limits those two?
Descent.
Descent. Very good. Um, this is another good diagram to be aware of. This one's not necessarily showing the path of the tear. I mean, we can trace the path of the tear, but you got kind of you've got your muscles up here, your superior rectus, because remember your rectus muscles are all around. You've got four rectus muscles that are just going kind of straight back, and then you've got your obliques here. And then, and it uses, remember, medial, like think middle of the head, lateral is the outside area, and then the superior is above and inferior is below. That kind of makes sense. And then with your obliques, which kind of turn the eye, not just in and out and up and down, which is what your those four rectus muscles do. This one kind of twists the eye a little bit. Not ridiculous, but does twist the eye a little bit. Your your canthus here, you got your lateral canthus and your medial canthus. You might also hear outer canthus, inner canthus. So again, that lateral and medial, those terms will help you with those as well. But up here, this little squishy looking thing, a little sponge looking thing, that's your lacrimal gland. And that's the one that whenever you have a stimuli, you cry or you get punched in the eye or hit in the eye with something, or, anytime something in your eye, that's the one that gets triggered. So he's kind of based off of stimulus. But he also helps to produce tears too. But you see these little tubes here, They come out, and the liquid of a tear kind of starts out near the outer canthus or your lateral canthus, and then our eyes kind of squeegee the water across, kind of washing that cornea and removing any debris, picking up um, the extra aqueous that was let out from the inside the eye, and squeezes into, there's two little holes at the top and the bottom of your eye, your punctums, or lacrimal punctums. But you got an inferior and or inferior on the bottom and a superior one on the top. So you have two little canals here that drain that out of the eye. The caniculi, what do they call them here? Lacrimal canal. I like that one even better description. But canicula is also another word you might see for that one. And so then it goes from here and deposits into the lacrimal sac. So, and that's up at the top. So, lacrimal sac, and then it drops down into the nasolacrimal duct. And I just always remembered that the lacrimal sac was first and the nasolacrimal duct is second, because the next place that we're leaving is out into the nose. So that kind of always helped me remember keeping those in order there. Yeah, and then these are just him, of course, all this is important. I mean, I could sit and talk about this for 3 hours. I'm not a super fan of this picture, because um, I don't know. I think it's kind of weird, because this medial rectus, I don't think that I don't know. Anyway, you still see the trochlea. That's what holds that those superior and inferior muscles in there, those obliques. And that holds that kind of like a little pulley system, so that they can all still go back to that one central place where they kind of originate from. Let's see. And here's more of a classic one. I did draw a nose so that for the medial side, lateral side, and you got your superior oblique. There's the little trochlea. Being familiar with all the different types of diagrams is important. So I would suggest going on to the internet and like looking around at different diagrams to kind of play around with and label. So looking at this diagram. I hate this diagram. What was this little part right here called that holds the superior oblique?
Trochlea.
There you go. I'll take it. And well, I just named the muscle. So, what's the rectus muscle on the bottom? This A one.
Inferior.
Inferior. So then that makes this top one the superior. All right. So it sounds like you guys are good with those. We're going to go over all of this. So, but yeah, I mean, this is all good information. It gives you examples of this. The one thing that I would recommend whenever you're given a prescription for this, like a power of the lens, and you've got to determine what was the refractive error, I would throw them up on an optical cross. That way you can see, because, when you look at this one, you might think, oh, well, that's compound because we've got a -150 and a +150. And so that means we got a minus and a plus. But when you put that on an optical cross, we get minus 150 in one meridian, and then we plus 50 from there, which actually only leaves us at minus 1. So the two powers on an optical cross for this minus 150 plus 50 is actually going to be minus 150 and minus 150. Just talk about them on an optical cross. So putting these on an optical cross is, some of them, like if it's minus and minus, it's only going to get more minus. If you put that on an optical cross, it's minus and minus. So you can kind of quickly look at that one. And the same thing for this one, you see that +2, don't go for, oh, that means it's compound because, or mixed astigmatism because one's minus, one's plus. When you actually look at what the power is on those meridians, you find out that it is indeed both of them are minus. And the same thing with these, the compound hyperopia. This one right here, you might look at that one and say, oh, well, that's mixed astigmatism. We got a plus and a minus. But when you put those on an optical cross, you get a plus 250 and a plus 50 because you add those two together, that plus 250 and the 2, you add those two together to get that other meridian. Whereas this is more of your true mixed astigmatism. When you put any of these on an optical cross, you're going to end up with one meridian plus and the other meridian minus. So if we looked at that one on an optical cross, and I really don't even care about what these axes are so much. If you just looking at these two powers, one meridian is a +1, then add these two together to get that other meridian, and you realize it's a -1. Does that make sense? And same thing for all of these. When you put these onto an optical cross, you'll get one minus and one plus. It's just best way to do it is to put those up there. So which one of these, and you can see saying right here, you got one meridian that's focusing before the retina, and then you've got the other meridian that's focusing after the retina. Which one is that?
Mixed.
It's mixed because one's in front, one's in the back. And when this one is in front and one is directly on the retina.
Simple. Simple myopic.
Mm-hmm. And then 2 behind is the compound. Yeah, all of this, I just think that these are really important and want to go all the way through them. So 186 miles per second. What is that one?
B.
B, the speed of light. And then how do you figure out what the speed of light? Well, what does this one say? 174, 1.74. What is an example of an index of refraction? Yeah. And D equals 1 over F in meters. That's the formula for dioptric power. And then 400 to 700 nanometers. That's the wavelength of visible light. All right. Yeah, I mean, all of this, and this goes back to some of your first year in theory. And the nominal power formula there, see, they're showing it with slightly different variables that he says DL. So you do need to be just aware of that. If you start seeing D or even an F, F1, F2, FN, those are all for just abbreviation for the curves on the front and the back and the power of the lens. And most of the time you're solving for what the back curves is going to be. They may give you questions where they say, they clock the lens on the front, they clock the lens on the back, and these are the two powers, and what is the power, expected nominal power of the lens. Then you just add the front plus the back. But if you need to solve for the back curves, then you've got to kind of change that formula around a little bit. We're going to go over that as well in a little bit more detail. But here's him talking about it. Vogel's rule, that's in lab, so we'll go over that one in lab. But just using that formula to figure out an approximate base curve. You've got one for plus lenses, spherical equivalent plus 6, and then another for minus lenses where you take half of the spherical equivalent plus 6. And that 6 just kind of is a remnant of previous lens technology, especially when they went to corrected curve and things like that back in the day, trying to make lenses better and better for people. So this is just kind of showing you if you do the oblique or the nominal power formula, these are the base curves that you end up coming with. This is actually a pretty important concept to understand, mainly for when you're actually selling a pair of glasses. Because if somebody comes in and they have, let's say, you have 3 customers or 4 customers or patients, whatever, and they all 4 have these prescriptions right here, to understand right away when you're looking at it, um, what kind of a curve are we going to have on that front surface so that you can kind of match that with the frame, because this person right here with this -4, -2 at 98, if they're over in the wrap sunglass section, this could be a bad thing, because wrap sunglasses are extremely curved. And what we should know about this, well, it's a minus power and it's a little bit high minus power. We've got a 4 and a 6 in these 2 meridians. And what that's going to leave us with is kind of a flatter curve on that front surface. And so the frame and the lens are always going to fight each other because the lens will be flat, the frame will be curved. It's kind of like old school square hole, round peg, or round peg, square hole. Anyway, kind of same thing. They will always be fighting each other. So then at the dispensing table, you've got a customer that constantly comes back saying the glasses just won't ever stay in shape. They keep, widening out and widening out. A lot of times that is because that lens to frame match wasn't good. So understanding how to figure out base curves by looking at these things, not so that you can call the lab and be like, yo, I calculated it and you better put a 9 on this prescription. You know what I mean? This is so that you can make the best for frame recommendation and product recommendation. And there are different techniques that you can do, or not techniques so much, but lens options that you can do to compensate for that, to make adjustments to still have like what they call kind of wrapped glasses, where they will compensate and get them into a higher curved lens without all the problems that are associated with just arbitrarily steepening the base curve. Because if this one's supposed to be on a 350, and you say, well, I'm going to put it on a 9, you're going to get atrocious base curves on the back, or curves on the back. You'll get, they would just be extremely high. And likewise, the most important thing is vision away from the very, very center of the lens is going to be pretty much unusable, just because the way light's behaving in there. So when the manufacturer says that the lens base curve is around this area, you need to stay in that area. It's not a good idea to start changing it to match the frame. So, Yeah, and then these I think are just kind of charts right here telling you approximately what you're looking at for base curves. The thing that I like about this one, base curves usually go from around a quarter up to, I would say, probably about 14 is as high as I've ever seen in my life. He's obviously saying right here that a base curve, 12, 25, that's extremely steep. If you think about zero, it's 100% flat. Then as we move up in plus power, the base curve steepens. And I think the best way, and we'll talk more about it, about this kind of this 626 is kind of like your baseline. If you think of a plano lens, according to Vogel's, is going to put you on a 6 base lens. Then anything steeper than 6 base, anything that goes up the line steeper, is going to mean we had a plus powered lens. Anything that goes flatter than that is going to mean we have a minus powered lens. So that's what is kind of nice about understanding these concepts, especially for when, somebody comes in and they have whatever prescription and ask you to help recommend the right frame. That's also why I've always abhorred, when a customer comes in, they just, oh, I'm just looking. It's good to still go over and say, all right, well, just keep in mind that your prescription does kind of, dictate what would be the best option for you as far as frame selection. So if you have a prescription I can peek at, or even looking at them, sometimes you can tell if a high minus is sitting in front of you because they've got, minimized eyes, and you can see how much it's minimized. So you kind of gauge what kind of lens you're talking about there. So if you see that, then you'd say, oh, well, that's a higher minus prescription. So you would want to tell them to kind of avoid those two frames that are too curvy. And this was where I was telling you about the ones where they can adjust and do like this freeform technology to adjust and make the lenses work. It's just kind of more complex curvature and freeform. So yeah, and with these, I drew out the like, a simple sphere or spherical power that's up here, sphere versus a cylinder. Cut from like a tennis ball versus astigmatism or a cylinder lens, which is kind of cut from a football. If I drew a curve over this, or if I took a lens clock to it and clocked that curve, it'd be the same curve all the way across. It's cut from a ball or a sphere. And when you see that on an optical cross, all the powers in the major meridians are all the same. And you see a lens power like this, -1 sphere. But when it comes to a cylinder lens, you've got two different curves. You can see this curve right here is flatter than this curve 90 degrees to it. And that would be an example of a spherocylinder lens where you've got, you might have the -1 would be right here versus the -2 in the cylinder part. So you see that right on the optical cross here. So like a -1, -1 at 90, you'd have that -1 going across here and your -2 going across here, more steeper. Versus a true cylinder lens, a true cylinder lens is more like, and I know lenses don't look like Coke cans, but that's just the best way I can think to do it, where the axis meridian, that 90 at plano, there's no power in the axis meridian, and 100% of the sill is located 90 degrees away. That still kind of pertains to here, except instead of having that true cylinder where we have a plano meridian, we actually have 1 diopter of power there. But this is the definition of a true cylinder where there's no power in the axis meridian, and there's 100% of the cylinder power 90 degrees away. Aspherics, we're going to talk about that in lab 2. Being able to switch between the two formats, transposition, I hope you all feel comfortable doing that without any problems. But just a couple of different, 3 different little steps. You just take and add the 2 meridians together here. So -1 and -1 is going to give us -2 for our new sphere. Then just change the sign of that sill, number stays the same, and then change the axis by 90 degrees, making sure you stay within that 90 or the 0 to 180. Optical crosses, I'm not a fan of this because it's, I don't know. I mean, you get it. It keeps going all the way across the lens. I mean, yeah. Uh, but yeah, you put the 1 meridian on there and label it. So yes, and this 45 always goes with that first number. So the axis always goes with that sphere. Axis always going with the sphere. So at 45, we have a -6. So we pick this for our 45. So 45 right in here, we have that -6. And then we're going to -3 more from that 6. So as we travel from here to here, we want to -3 more, which ends up with a total of -9. All right, and so looking at this one, we would just do 60, right? 60, we got a -4. So we'll use this as our 60. So this would be 60, we'd have -4. Then we're going to go -1 as we travel from one meridian to the other. So we would end up with the -5. And you see that the -5 and the -4, those end up being the 2 powers on the cross. And these end up being the 2 meridians that are associated with those. So, if you just look at these two, when you add those two together, that -4 and -1, you get that -5. When you add -5 and +1 together, you get that -4. So there's a relationship that's happening there. And if you get something that doesn't equal out to one of these 2 front numbers, then something's gone wrong. You need to do it over. And taking it off the optical cross. So if I want to take this one off in plus cylinder form, then I want to make sure that I choose one of these meridians that's going to result in, when I go to the other one, that I'm going in plus cylinder. So if I choose this -3 with an axis of 30 for my sphere and axis, then if I go from that -3 to -4, how far did I go? And again, think money. So I had -$3 when I started the day, and at the end of the day, I was in debt by $4. I spent an extra dollar, right? So then that would put that one, if I take the -3 first, then that would be -3 -1 at 30. So if I want it in plus cylinder form, if I go from a -4 to a -3, then you see how I gained a dollar. Start out with $4 in debt, and by the end of the day, I was $3 in debt. Then I gained a dollar. So -4 plus 1 at axis 120. Prism. Here's what it looks kind of like. Well, this is what basically it looks like in the prescription. You've got your regular prescription here. You might have an add power, whatnot, but then you've got your prism, and this one's 1 base up and 1 base out and 2 base up. Are we balancing prism here? Let's see. Yeah, and here this imaging is showing you that if you line the eye up and you see how this person, where their eye goes through, is looking, they got base out prism and base out prism. So you can see that kind of superimposed over top of the eye. So they're experiencing base out and base out. And since the object moves towards the apex, the image is going to appear shifted nasally. So that means the eye is going to end up trying to turn more to see that object where it appears. Let's see. And then they're showing, that's the inside. All right, and then this diagram is showing you the difference between a 1 diopter and a 3 diopter, just kind of showing you that the larger that prism amount is, the more that object appears to move from its original location. So if you got 1 diopter prism, we have just this amount of movement, but if they were looking through 3 diopters of prism, we'd have much more movement there. So just kind of showing you concepts with that. Optical center versus major reference point. Um, yeah, so this is showing if the person's looking through the OC, then they're looking through on a minus lens, they're looking through the apex point where the two apexes meet. And with a plus lens, if they're looking through the OC, then they're looking through the place where the two bases meet, because that's the shape of the lens. Minus is thinner in the center and plus is thicker in the center. But if we move I'm sorry, I see the canthus right there now, that inner canthus here. So if this is a right eye, this I don't like about it, this diagram. I'm sorry. This shouldn't be like this. It's base out if the nose is over here. It's base in if this is just the right eye or the, what is that? The left eye, right eye, left eye. So that's how this is how I drew over top of it for it. Cause I don't know, the other diagrams were, oh, and then he switches them up here. But anyway, sorry. But if this was the right eye and this was the left eye, and they're looking through, and their nose is there in the center, and if that OC is moved out, then they're experiencing base in prism. Versus if the OC is moved out, and this is a left eye, there's the nose, and the OC is moved out, then they experience base out prism. And then Prentice rule, I think everybody is really familiar with that formula, using that to figuring out little d times big D. So the distance or the distance from the OC, if you want to think about it like that. And the dioptric power will give you the prismatic effect. So just using that. The one thing I want to point out is when you're dealing with the big D, the dioptric power, you want to make sure that you're working in you're using the power in the correct meridian, because we talked about that before. But when you're dealing with prism, you've got directions like base up and base down and base in and base out. And base up and down are always in the vertical meridian. So power in the 90, always. And anytime you're dealing with horizontal prism or base in and base out, you're dealing with power at the 180. So whenever you need to use Prentice rule to plug in what this dioptric power is, you have to make sure that you think, what kind of prism am I dealing with? On the flip side of that, if you're talking about the patient or person looks down, when they look down, again, same thing as looking up or looking down, or base up and base down, that kind of thing. All those are up and down. So that would make you say, okay, the power at the 90. If the person looks to the right or to the left, or if the PDs are off, the OC is displaced to the right or to the left. Any of those are all talking about horizontal prism, and you need to make sure that you're doing the power at 180 to plug in here. Doing the oblique or the spherical equivalent won't work for you, and just using whatever the sphere power is, or the you have to find out what particular power is at that particular meridian, because that's how the lens is going to, or the light will end up behaving as it goes through that lens. For compounding and canceling effects, when they're base up and base up, those are going in the same direction. And I'm literally doing my arms like I do in class. But when you got, let me see if my camera's gonna work. Do y'all see me?
No.
No. Okay. Sorry. Well, then it's not gonna. Yeah, so if you've got base up and base up, those are going in the same direction. So the eyes are headed both up. So those would be a canceling effect. Base down and base down, those are headed in the same direction. Those are a canceling effect. And when you have for horizontal, it's opposite. The opposite of base in and base out is what causes a canceling effect. If you think about a minus wearer, this is where I need to draw. If you think about a minus lens wearer, let me do that. If you think about a minus lens wearer, then when that person looks to the right of their optical centers, then they experience a yeah, I need to draw it because that's just too much. Yeah, I strongly recommend drawing them out. Just trying to think of it till you get used to it. It's just too much. But anyway, so opposite base directions horizontally versus like base directions vertically are all canceling. So you subtract those amounts. This is a really important concept too when we're doing slab off prisms, because usually we have to either compound or cancel those amounts. And granted, those are in the vertical only really, but let's see. And then with compounding effect, a compounding effect means we're gonna, they're gonna the eyes are gonna go basically in opposite directions. So if we have base up and base down, that's gonna split the eyes. One's going up, one's going down. And so those amounts would be added together. Those prism amounts would be added together. And compounding for horizontal is like base direction. So it kind of just does a switcheroo on you, which usually causes issues for the learner because you just gotta remember which ones. But this is definitely an important concept. Yeah, I said that. PD questions are done with power at 180. OC questions are done with power at 90. If you're given a problem concerning patient PD and an RX of something like -1, -1.25 at 90, you must do flat transposition and find the power of 180 to solve the problem. Yeah, the only reason you can do flat transposition here is because this prescription is at 90. So anytime it's at 90 or 180, you can always do flat transposition just to figure out what power is at the 90 or 180, whichever one you're needing. Because if you look at this, okay, at 90, we've got a -1, right? But what if I said, well, what's the power at 180? Then you could just flat transpose, or basically just add those two together. So -1 minus a -1.25 is going to end up with a power of -2.25 at 180. So you can like really quickly do them this way. If not, if you're given a prescription that has any other axis, then you're going to have to do that oblique meridian formula or use some of those. I think he does cover that in here at some point. But use those little, remember the percent of the sill, that 25% of the sill, 50% of the sill, 75% of the sill with those. I think he does go over that, so we'll do that one. This is a very common, you're going to see this probably on your those mock exams as well, but a pair of glasses is made by the lab for a patient PD of 52 when the actual PD is 58. So a difference of 6 or 3 in each eye. And the order was completed correctly, but the lab made an error to determine the amount of prism experienced by the wearer. Yeah, we're just using Prentice rule. I'm not a big fan of that one, but you guys know your Prentice rule well enough. So we look at how much the error is per eye. And prescription is this. So we could either use 6 or 3 with the power if we want to figure out the total error or the each eye error. And then with this one, what power do we need to work with? So we've got a -1, -150 at 80 for, or 180 for OU for both lenses. So if this was the problem, patient size at 52, but the PD, the actual, wait, the lab for a patient PD is 62. The lab was made. So the OCs are at 52, but the patient's eyes are at 58. So we're 3 millimeters off in each eye, right? Just subtract the 2 and you get 6, or subtract the 58 and 52, and you get 6 divided by 2 and you get 3. And then since this is a PD issue, what meridian power do we need to use in Prentice rule? It's a PD issue. PD 180, right? I hope everybody said 180. So since it's a PD issue, we're going to use the 180. So looking at this, what's my power at 180? -1, right? Because you see, we're like, okay, well, there's 180 right there. Boom, -1. So we take the -1 and we multiply that by the 3, and we get 3, right? 1 times 3 is 3. Divide that by 10, and we come up with 0.3 right here, right? 0.3. That's per eye because we used the 3 for each eye. So that's per eye. So we could double that and find out that 6 diopters OU, 0.6 diopters OU. Greg has a really nice pergola he's building out there. Sorry, yeah, so we'll do some more of those too, but that's just kind of showing you that. And then he's got more examples of it right here. So do you guys feel comfortable with these? We got a monocular PD. So what meridian are we dealing with? The error is in decentration, and we're talking about PDs. What power meridian do we need?
180.
Yep, 180 because we're dealing with PDs. So the power at 180. So when we get down here, we'll be, what's the power at 180? And you can see it right away because we've got 180 and 180. So we're working with a -2 and a -3 as far as the power in Prentice rule that we're going to be using. And so we got a monocular PD distance of 32 and 34. The frame pupillary distance is 70. And an optician error in which no decentration occurred. When no decentration occurs, where does the OC end up being? Where does it start out at? Where does the optical...
Is it in the middle?
In the middle, okay. Yeah, in the middle of what? What's in the middle of the frame?
The beam measurement.
Was it what?
Like half of the B measurement?
That's for vertical, yeah. So, but what else? What would it be for horizontal? What's
Oh,
the middle of the box or the middle of the frame opening?
it's not frame PD.
You're not that far from where you want to be, but I'm looking for boxing center. And you're getting the frame PD comes from that boxing center, but yes, but your boxing center, the very, very center, the boxing center is the very, very center horizontally and vertically. So if you don't do any decentration to move the optical center to position with the eye, then it ends up staying right there at the boxing center. And when you look at almost everybody, remember we were doing it in class, when you look at everybody, most everybody's eyes are just inset just a little bit and they're up a little bit from the boxing center of the frame. So the fact that this says when no decentration occurred, if we can find out where that point is using that right there, because you've got your frame PD is 70. So we know that the distance between one boxing center to the other boxing center is 70 millimeters. But then we also know that our patient's eyes are at 32 and 34. So what would we need to do? We would need to divide that 70 in half, right? So that we can start working with the kind of that monocular boxing center distance. So 70 divided by 2 is 35. And that's what you're seeing right down here. So you see the 35 and the 35, that's the frame PD divided by 2, because these are monocular measurements that aren't symmetrical. So we're going to get different values for each eye. So then we take half the frame PD and we subtract the right lens or the right eye PD, and we come up with a 3 millimeters that it should have been decentered, because remember it said no decentration occurred. So it should have been decentered 3 millimeters, but no decentration occurred. So that's what lets us know that we need to use that 3 millimeters in Prentice rule, because that's the distance away from where we need to be. The eye is looking 3 millimeters away from where the optical center is. So then we put that into Prentice rule and we say 3 millimeters times the 2 diopter power divided by 10 gives us 0.6 diopters of prism. So that error from not decentering this lens caused a little over a half of a diopter of error in the right eye horizontally. And then we just repeat the same thing for the left eye. We've got our frame PD minus the patient's left eye, and that results in 1 millimeter. So we're only off 1 millimeter in the left eye. Okay. You can add these two together and we're 4 millimeters off total. If you see the 3, I don't know if it's going to, no, it's not going to let me do that. But if you see the 3 millimeters here and the 1 millimeters, that was 4 millimeters total, but because each one was slightly different, we ended up with different millimeter errors here. So anyway, just pointing that out. So we take that 1 millimeter difference and we multiply, or there it is, 1 millimeter difference multiplied by the power in the 180, because we're talking PD. And then that comes up with 0.3. So with this one, wish I could just draw right on here. But with this one, if it's a minus lens and this happens, what kind of prism is experienced? Base in or base out? I mean, it says it right down here, but do you understand why? Basically, you would just draw out the lenses, put your little horizontal X's on there to represent the horizontal. Hold on. All right, so y'all can see that. Okay. So you basically just kind of draw your lenses out. We got a minus lens for both of them, and we're drawing them in the 180, right? In that 0, 180, because we're dealing with PD. Here's where the actual OCs are. And if you remember what was it was 32/34 was our patient PD. And then we had a 70 frame PD. And remember when we calculated that, we had 3 millimeters of error and 1 millimeter of error. That was the OD and the OS. All right, so we've got 3 millimeters of error here. And remember, the problem prompted us that no decentration was performed, right? So where do you think that the eyes are with respect to that? Do you think that they are in here or out here?
Out.
You think the eyes are out?
Oh, not the eyes, but the frame PD is out. So the eyes are in.
Correct. Yes. Yes, because the frame PD is out, but the eyes are in. So they are actually experiencing this, which is base in and base in. Base in and base in. And another way to look at it is when we took this and we divided this by 2, we got 35, right? So 35, because it said there was no decentration performed, so 35 is exactly where this OC is at, right? Horizontally, the measurement we can think of is 35. And then these two guys, the patient's eyes, are slightly in from that. And that's how we knew that we would mark in here for where the eye is. And so they ended up experiencing base in prism from this. Does that make sense?
It makes sense when you do it. Sometimes in the questions, it's like abstract. What moved, which one, and then that's where I kind of flip upside down. So I don't know what it is, what drawing I need to do. Like always keep the circle, the OC, and then X where the new PD is, or the error, but
Yeah,
something didn't check.
I would try to keep up with where the eye is going. Like use the information that you've been given
Mhm.
to try to figure out where the eye went, because where the eye went is how you're going to decide where your prism is, because the prism is relative to the eye, right? And
Mhm.
so if the lens, let's say the lens is moved up, let's say lens moved up, all right, and then we through whatever find out that we're dealing with, let's say, um, a minus lens. Okay, we can look at this. Well, moved up lets us know that we should be in what meridian? What meridian are we dealing with for power?
90.
Mm-hmm. So this is 180. Add them both together to get 9 at 90. So we have a -3. So we know we're dealing with a minus lens. So I know that I'm going to draw my lens like this. And you can start there. And then this is the OC. And the lens, we were told, moved up. So if you assume the eye was here, but the lens itself was moved up, then where is the eye in the end? Let me see if I don't know if I can grab all this. I'm not taking the OC, unfortunately. Boom. So that shows you the lens moved up, and you see what kind of prism does that cause. There's the OC. See, the OC is moved up. So the OC was moved up. So right here is where the eye stayed where it was. So you can see then it's base down prism.
Okay.
Versus if you're told that the lens, let's see if I can grab all that. If the lens was supposed to be here, because this is ideal, no prism, but the lens moves down, the OC was moved down, then you see in this particular lens, we got a minus lens. So the eye ends up being base up prism when it comes to that.
Sometimes they will say in a question, the eye looked above, right?
Mm-hmm.
Or the eye looked below. I think.
Yes. And in those are even easier because with those, you could just say, okay, the eye, there's my OC, there's my lens. And then you just assume that the eye starts out, ideally, we want the eye and the OC to be in the same spot. So you said, oh, the eye looks up. Well, if it looks up, it starts here and it looked up. So boom, that puts us here, right? So that would end up being base up prism, right? And if and that's if they look up. But if they look down, then they move down there, right? Because they start out at the OC and then they look down. So that moves them, and that would be base down. And then the same concept is applied if we got a plus lens in the 90. Again, our OC is right here, and this is where we want our eye to be. But if that person looks up, what kind of prism?
Face down.
Face down when they look up. But if they look down,
Face up.
face up.
What can I ask a question though?
Absolutely.
Above, when we go back to the horizontal one where you had base in, I don't remember what the answer was from the original question when you went and drew this out. Like, I don't know how to explain what I mean, but why you decided to put your X's there and everything, I'm just not sure.
Okay.
I'm not
Yeah.
really explaining it well, but like I know how we just did all the ones that we went over base up, base down, but whenever you got the answer to that question and then you drew it out, what was the original answer? Do you know what I mean? Like we had, I don't know.
Are you referring to this?
I don't remember the answer. Whatever you got, you had to have gotten an answer right to then have drawn that. Yes.
Like this?
So it was 0.9.
Yeah, total, because we had 0.6 in the right eye and 0.3 in the left eye, and base in compounds because the eyes are going in different directions. And so they add those two together and get 0.9 for the total. So
And
the total.
You knew it was 0.9, and then you went to draw the photo.
Yes, that's what I would do. Yeah. Well, sort of, because with this one, when you first do the problem, you're finding, okay, well, how much is the millimeter difference? Because we're building our Prentice rule formula, right? So we need to know from this information, what's that millimeter difference? How far is the OC from where it's supposed to be? We got to know that. So you figure that out. And then you take that millimeter difference and you plug it into Prentice rule with the power at the correct meridian, right? And this is horizontal, so we're 180, so we multiply it by 2, and that's how we come up with that. Same thing over here. We found that millimeter difference. Then we did Prentice rule. Then you do your base directions because you kind of can't decide whether these are going to be added or subtracted until you know what those base directions are going to be.
Yeah, I just don't know how I understand how we got to 0.6 and I understand
Okay.
how we get to 0.3.
Okay.
But then I don't know. And like I could draw what, like, how do you know? I don't know how you got base in. I just don't know. I don't know how you knew that or how they knew that in this answer. I'm not getting it.
Okay, well, and it is a little cryptic. I think that's where you guys are talking about it's kind of cryptic in figuring out what happened. What was the problem? And in this one, this is a good example of one that's kind of cryptic because right here we've got it highlighted. It says no decentration occurred. So in order to know that, what was the error then? You have to know that starts at the frame boxing center.
Mm-hmm.
Let me see. Yeah, you have to know that that's at that frame boxing center. Let's see. I've got
And
it.
we're in a negative prescription, so it's hourglass shaped sideways because we're in 180.
Mm-hmm.
Okay, I think I kind of get it. All right.
Well, let me go back to the stop sharing here. Share here. Share screen. Here, okay, so this is a boxing system. And if we don't do any decentration, we're not telling it anything different, meaning we're not going to place that lens anywhere different. Let me draw a lens here. And let me take the 3 lensometer spots, right? And that's our OC, right? Okay. Everybody following me on that? Okay. So we take this lens and I hope it's big enough for cutout. It's not going to be, but anyway, let me just resize it. It's a ridiculous size lens, but whatever. You know what I'm talking about. If we don't do any decentration, the lens starts out right here and stays here. I know there's a lot of lines on this, but do you see?
Basically, it's kind of like the concept of the eye is looking over here, right? Like the eye is looking.
Yeah,
The
yeah,
lens didn't move, so it's the eye that's looking.
yes. Yes, because since we didn't do any decentration is us moving the lens wherever the eye is positioned at, right? And we do a horizontal movement, either in or out, and we do a vertical, either up or down, right, of the OC based off of wherever the eye is. If we don't do any decentration, then we end up with an optical center at the boxing center, at this center point of the frame. And this particular question told us that no decentration occurred. So if no decentration occurred, then we can, when we draw our picture out, we can say, oh, okay, well, here's
where it was. That just stayed exactly like that, but our eye was looking like our eye is somewhere else. I think
yes, very much so. Yes, you've got that concept is right. Because here it is. I tried to draw it in something that was maybe something you can see. So there's our lens. Okay, there's our minus lens. Oh, stay away from that drawing. So there's, sorry, y'all. Okay, so there's what we've got. But we need to technically move it in. Remember when we calculated that it was supposed to be 3 millimeters in. So the eye is somewhere in here, 3 millimeters. But if we don't move, then the eye ends up being right here. And you can see that base in prism that results. Did that diagram just get too crazy? Does that make sense?
Yeah.
Yeah, that helps that you can move it.
Yeah, and then the same thing happened over here. The eye was we were supposed to decenter 1 millimeters in, but we didn't. So keep your eye at where this optical center is right now. So right about there, right? You see where that's crossing? And you see how it's just where the eye is just inside nasal too. But since we didn't do any decentration, we ended up with this kind of a setup where the OC was at the boxing center and the eye was actually right about here somewhere. And so that's how we end up with that base in prism right here. Does that make sense?
Mm-hmm.
Okay, so let me try to go back and share. All right, are y'all seeing the other screen? Are y'all seeing my? No, you're not, are you?
No, I
Share.
feel like Greg's garage.
All right, have we gone out of Greg's garage?
Yeah,
All right, so now you're seeing my screen.
yeah.
Greg, you can't hide the money, man. Look at your fancy garage, beautiful pergola. He's muted. He's having a full-blown conversation with us muted.
I keep muted so you guys don't hear the impact drill going, but
Yeah,
no,
well, yeah.
I'm just working and listening,
Okay.
building my gazebo. No worries.
All right. So yeah, so this one, because it had the no decentration, that's how we knew that it was going to stay at the boxing center and what helped us draw the image out. So draw the lens out, because that's where you would get to. You'd get this point right here. You'd figure out your millimeter difference, figure out what power are we going to be using in Prentice rule, calculate Prentice rule out. But then when you get to this point to decide between the two lenses, whether these are going to compound or cancel, you are going to start drawing out your prisms. And draw your lenses out first, because you're like, okay, well, I got a -2, we're in the 180, so I'm gonna draw my minus lenses along the 180. And then there's where my OCs are. And then where are my eyes? If whatever the situation that the question's telling me has occurred, then where'd the OC go in reference to where the eyes are? And it's the same with whether they look there or whether it's being moved. You just have to keep straight of, where the OC is and where the eye ends up being. Whether it was a movement or an error in placement like this one has. Let's see if there's any more. Why doesn't he put more? That would have been a good one to go over, huh? Here we go. Here's another one. Okay. Pair of glasses was made by the lab for a patient with a 56 when the actual patient PD is 64. So actual patient PD, you should be translating that as my eyes, where the eyes are. A pair of glasses was made by the lab for a patient PD of, okay, so it was made by the lab for a patient PD of 56. That is long for basically glasses PD. So where the actual OCs are in the lens. You guys remember when you're in class and you are using lensometers and you guys put the lenses in there and you spot the OCs and then you take it out and you've got those 3 little spots on each of the lenses. And then when I ask you to measure the PD of the glasses, you measure the distance between those 2 center spots. That's kind of the glasses PD. They have their own PD, and ideally we want it to be the same as the patient PD. And if it's not, then we have this prismatic error happening. And that's where it leads us to doing the Prentice rule formula to figure out what that prism is. So this is made for a PD of 56, but the patient's actual eyes are sitting at 64. We just subtract those two and we can come up with, they've got a total difference of 8 millimeters total between the eyes, or divide it by 4, or divide it by 2 to look at each eye. So we know that each eye has 4 millimeters of error. So it's off by 4 millimeters. And then it says to determine the amount of prism experienced by a wearer with lenses which have been decentered 4 millimeters too much nasally. Okay. They're giving you that information. You would technically be able to figure that out by looking at the lab made it with a PD of 56, but the patient's PD is 64. Let's see, let's go. Back here. Okay. So we've got another one here, and the pair has a PD of 56, and the patient has a PD of 64. All right, you can subtract these two to come up with 8 millimeters of error total, or divide that by 2 to come up with 4 millimeters per eye of error. Okay, so that's our little d in Prentice rule. All right. Let me see, where was I trying to show y'all? Let's get some of this off of here. We don't need all this for this. All right. Okay, so the patient's PD is at 56. I'm sorry. The glasses PD is at 56 and the patient's PD is at 64. I don't even think we need this. Oop. All right. Try to find a color that'll contrast. There we go. Maybe this one. Okay. So, well, let's draw it the way you guys would have to draw it, because you ain't gonna have these drawings. Drop them away. So you'd have something like this. So you'd sketch this out and you say, okay, well, the pair, where's the pair PD is at 56 versus the patient's PD at 64. So what does this tell you? The distance that we're measuring from here is like from here to here. So we're measuring kind of from here to here. So if we say, okay, this is going to be the 56. That's going to be the pairs PD. So that means that's where the optical centers are. And this lens, we had of course, we have a +5 minus 175 at axis 180 OU. So each of the eyes are that way. What meridian are we dealing with? We're having a PD issue, so we're dealing with what meridian?
180.
So we've got a 5 in both lenses, okay? So, and it's a +5. So if this right here is my 56 millimeters, which is my pair PD, that means my OCs are at 56 millimeters on a plus lens. So my lens is going to look like this, right? And then my patient's eyes are actually at 64 millimeters. So are my patient's eyes nasal to the OC or temporal to the OC?
I want to say temporal, but I'm not sure.
You are right, because if this measurement here is 56, OCs are 56 millimeters apart, but my patient's eye is at 64, then that puts us somewhere out here, right? Because that would be 64. And then you see what kind of base prism do we have with this when it's a plus lens with this error. Base of the prism right here. Where's the eye going to be looking through? Remember, this is the patient's PD, so we're looking through their eyes, looking through a point 64 millimeters versus the OCs at 56. So when they look through here, they are experiencing what kind of prism?
Basin.
That makes sense?
Yeah.
If
So
this
just
had
to be sure, if it's a -5, it would have been base out, right?
correct, I was just about to do that with all this, but we know that this is at 180, so who cares about all that? But yes, this guy would be, if he was minus, then all of a sudden we'd have the same situation. Let's pick a different color. OCs, OC, right? Is that too much? You're all on top of it?
Yeah.
It's okay, or is it too much? A little much? It is a little much, isn't it? So sketch it out again, okay? So this time we got minus, okay? Here's my OCs. These OCs are at 56, and my patient's eyes are at 64, so they're out from there, right? Because if we measured from here to here, we could say that's 64. And yes, that would be base out and base out. So you see the difference between them. Same scenario, but if you've got a +5 versus a -5.
Mm-hmm.
All right. And if this person is looking through these glasses, when this person is looking through these glasses, what's going to happen to the eye? Because the prism, right? So here's where the eye is, and they've got base out prism. But what's going to happen is, remember, the image is shifted towards the apex. So their eye is going to force their eyes to kind of converge. And that's not necessarily a comfortable thing when you're not trying to converge. If you're looking at something in the distance and your eyes are trying to pull in and converge, that's not going to feel very comfortable. So that's how you can see that this is compounding, because we're not going in the same direction. The eyes are going to be going in, even though they're going in the same direction together, they're not they're not aligned in the same direction. This one shows it a little bit better, I think. A plus lens shows what I'm trying to get across here. We had our patient's eyes are out from the center. So this person, their eye is going to be sent out over this way, and then this eye is going to be sent out over this way, and as opposed to what we would ideally like, same direction, same point, same moving in the same direction here. But the eye is going to be deviated outward a little bit, right? And you can see how you compound all that. I know it looks kind of like a little smiley frog, but you see that we've kind of, that adds to it. So this is both of these were base in OU, right? So we had base in and base in, and this is a compounding thing. So when it compounds, we add them together. So that's why I can only just remember this last one that we did when we had the prism that was compounding, and that's why we added that together to find the total imbalance was 0.9. And it would be the same thing here if we had a 0.3 and a 0.6 OD and OS. If that's how much this ended up causing, then these two would compound. And we would have a total of 0.9 base out prism versus this one, which was a total of base in prism. And this is where the drawing maybe does get a little bit hairy, because this is where it kind of differs. This is unnatural. The eyes don't like to go in opposite directions. Converging is a little bit more natural, but I dare any of you guys to try to look out and out, like at the same time. You can't do that. And instead, when we look through a pair of glasses, and let's say they're minus, right? Normally, the person's eyes are looking through the OCs, but let's say this person looks left. That's their nose. Looks left. They're looking at us, and if they look left, they're going to be looking over this way, right? Yeah. So if they look left, then where does the eye go? Look at each one. So here's the OC. If they look left, then that's going to put the eye right here. If this is the OC and they look left, that's going to put the eye right through here. Now this is a canceling thing, because the eye is going to be shot over this way, just like this one was, right? But also with this one, the eye is going to be shot over this way. So do you see how this net effect here is not getting any larger? So this one just cancels out. So if we had 0.3 diopters in this one and 0.6 diopters in this one, then we would need to subtract these. Does that make sense?
Yeah, and it's base out, right? Like if
Oh, yes. So you're saying, like, if you subtract these and you take
if we went from your X, the base direction is base out, right?
for this eye it is. What's this one though? This the right eye. This one.
Oh, base in.
Yeah, that eye is experiencing base in prism. So we've got base in and base out. And what ends up happening is the eye goes this way and this eye goes in the same direction. So that's why these would be considered canceling.
Yeah, I forget about the nose being there, and then I forget. Okay. Yeah, it would be base in. Okay. And base
Right.
out.
So we've got base in and base out, but if they're canceling, then we're going to take one and subtract it from the other. This is a bad example because it ends up being a same number as is in the equation, but we subtract these. This amount is what we have left over. This is our unwanted prism amount or error, unwanted prism error. So we have 0.3, and which I had the excessive amount of base of prism.
The left.
The left eye did. So this 0.3 is in the left, and we would say we have in the left eye, we have 0.3 base out of unwanted prism error because they canceled. Versus this one over here, where we had OC error. You can't, the eyes can't ever look out there like that. They just don't. The most you're going to get is them looking in at the same time. You know, like if this is a real scenario, if a minus person is supposed to be looking through the OCs, but then let's say they converge to read up close, then that means their eyes move into here, right? And they experience base in and base in. And these are it's a compounding experience because they're going in opposite directions of each other as opposed to the same direction. These are going in opposite base directions or opposite directions, the eyes are, as opposed to when they cancel and go the same. So do you see here, when we had this one where they looked to the left, we ended up with 0.3 base out, leftover, unwanted. But with this error, we had both eyes, the PDs were off, but it was a compounding amount. And so that's why we ended up adding those two together, and we come up with a total of 0.9 versus that 0.3 because one was compounding versus one was canceling. Does that make sense? Let's see. Where did I have this? I attached this as feedback in you guys's Mary, I'm sorry you're on. Okay, there we go. I can move you off. Okay. All right. You were just in my way. No, so I attached this to everybody's feedback, or most, I think I put it in everybody's, regardless of whether you were struggling with these. But this is kind of the steps that you do when you get to the point where you're determining the prism. Because remember, before that, if you're doing anything else, like if you're doing where you got to do Prentice rule, you've got to, you know, find out what the power is, and then you got to figure out what the little d is and divide it, and then you come up with some type of a prism amount. Then this is where it starts right after that. This is where you can, and I don't think you'll ever go wrong. You draw the lens in the appropriate meridian and mark the OCs. So all of these, I start out by taking the lens and I draw it in the appropriate meridian, right? And then I mark my OC. And then I say, well, what happened then? Did the eye look somewhere, or was the lens moved somewhere? So if the like this one is saying if the OC is too low, so that means the OC is here. If it's too low, then that means the eye ended up here, base up prism for a minus lens. So that would be the OC is too low and the eye is below, or the OC is below the eye, versus the same situation is going to end up resulting in base up prism would be if the wearer, does that say talks? Wow, that should say looks. All right. But the wearer looks above the OC, then that would be the same resulting prism. So again, just draw your lens out, draw the style you need, mark your OC, and then decide, well, was the OC, what happened? So the OC is too low, then boom, that puts me up here, base up. Is the wearer's eye is below the OC? Wait, below the eye. No, this is saying the OC is below the eye. So if the OC is below the eye, then that means here the wearer base up. Or if my wearer looks above the OC, then there's the OC and they look up, base up. All those, every single one of those is going to end up with the same resulting prism. And then you have the same thing with these here. The wearer looks versus the other one. Then when you get down into these are a little bit more convoluted because you have to figure out whether you're dealing with a right eye or a left eye. That's why I just drew both of them out. But if the OC is too wide or too temporal, again, there's our OCs. And if it's too wide or too temporal, that means that the eyes are sitting nasal to it. Would be also the same thing as if the wearer looks nasal to the OC. Then this minus lens, they would be experiencing base in prism. Versus if the OCs are too narrow or too nasal, so there's our OCs, and they are too narrow or too nasal, would let us know that our patient's eyes are out from there, out from the OC. And in this minus lens, that results in base out in each lens, base out. If the wearer looks temporal to the OC, all right, and I had to kind of flex that one because again, the eyes don't naturally do that. But if the wearer looks temporal to the OC, and this is whether you're dealing with a right or a left, you kind of just, okay, if the wearer looks temporal to the OC and it's the right eye, then here's my right eye, here's my OC, or there's my OCs, and the wearer's looking through here. And you would do the same thing for when it's just when you're asked about a left eye, if they're looking or if the OCs are too nasal, then there's my lens, here's my OC, eyes are gonna be out there. So again, all of these OC too narrow, too nasal, and the wearer looks temporal to the OC are all saying the exact same thing, and they're going to end up with, for a minus lens, base out prism. And then it's exactly the opposite when it comes to a plus lens. So when you get the plus lens, OCs are too wide. Well, there's my OCs. Too wide means eyes are in. So in this plus lens, eyes are going to experience base out prism. And when the OCs are too narrow or too nasal, or where looks temporal to the OC, then here's my OCs. They are too narrow or too nasal, so that means my eyes are out here, and that, boom, would be base in and base in for each one of those. Do you guys feel a little bit better about Prism? Prism base direction is pretty big on the exam, the ABO as well too. So do y'all feel okay with that one? A little bit more at least, hopefully.
Yeah, probably just keep practicing it, because when it makes sense looking at it is when it's, I don't know, when the question is on a test, a practice test or something. I get the right prism, but that one will sometimes get me off, and I can see it after I do it, but it's just practice, probably making sure I'm 100% on it.
Yeah, it is, and it's just the more you do it, the better you get at it. So it's just, yeah, practice. and getting more comfortable drawing them and kind of understanding. Because I
Mhm.
mean, if you think about it though, I mean, this kind of thing happens at work, you know, this in particular, this all this down here happens a lot. Basically, you know, somebody accidentally, we had a you know, somebody was supposed to decenter something 5 millimeters, but accidentally decentered it 2 millimeters. And so, what kind of error are we looking at? Well, we're talking I shouldn't have did that. So 5 millimeters was what we were supposed to decenter it, but it was actually decentered 2 millimeters. So how much error are we looking at? How far off are we? We just subtract those two. Does everybody see that? So the error that we had was 3 millimeters. And then
Mhm.
that's what's going to be used in Prentice rule as our little d.
Mhm.
And then since we're talking about horizontal decentration, we figure out whatever our power is at 180 and use that to come up with that. But then drawing it out, so let's say we had a -3 OU at the 180. That's too many threes. Let's say it was 4. So we had a -4. What kind of prism are we dealing with? So we could calculate that. We have everything we know. We could say 3 times 4 divided by 10 gives us whatever. But what's the base direction of the prism? We got minus lenses, right? So let's start out here. Boom, boom. Draw my minus. Draw my minus. Where's my OCs? Right here. And I am 3 millimeters away from where I'm supposed to be. We were supposed to decenter 5 millimeters in, but what we actually ended up doing was 2 millimeters. So where are my eyes at? Are they A or B? Did they move to, are my eyes nasal or temporal to the OC? If I was supposed to do 5 millimeters, but the actual decentration was 2.
Is it A?
So if we're supposed to go in 5, but we went in 2, yes, it is. Because we should have went in all the way to 5, but we didn't. We only went in 2. So our eyes, you can think of it, our eyes were at 5, but this was at 2. Very good, Mary. So then we'd end up with base N prism for this. And base N for each eye, is that compounding or canceling?
Cancel.
Mm-hmm. And if I did my math right real quick just a second ago, I ended up with 1.2 base N for the right and 1 point. Boy, that error was bad. 3 times 4 diopters of power. Yeah, that's right. So 1.2, and you said this is compounding, right? So we would add those two together, and we come up with a total error of 2.4 base N. And this would be very bad. We would definitely not dispense this. Because we had 3 millimeters in error in each eye. So the total error was 6, of course, right? And ANSI allows us to be off by how many millimeters in the PD? Ooh, that one's a left one. Left hook out of where? How much does ANSI allow us to be off in PD? Binocular PD. When you guys
Is it-
all answer at the same time, I can't hear any of you.
Is it 1?
One is vertical. I'll give you that. One is a vertical error, so you're allowed to be off by 1 millimeter vertically. but
point-
we're a 2 point what?
2.5.
2.5. Very good. That is our PD error that ANSI allows us. So if this PD error was 6 millimeters total, does that pass or fail?
Fail.
Big old fail. And then when we figured out how much prism we had, do you remember how much ANSI allows us to be off for prism horizontally?
No.
Is it 0.33?
0.33 is the
vertical.
Vertical, yeah. 1 millimeter.
0.67 is horizontal.
Yes, 0.67. Think about it, because with vertical, it's all one eye. You're allowed one eye, so you get 1 millimeter error and you get 0.33. And that's all just vertical, right? But horizontal, you have the two eyes, and we're doing a binocular amount. So if you kind of look at this 0.67, it's actually like 0.33 just twice. And remember, we always have that magic 5 that we drop off of everything. I guess that's the way you can think about it with that. But why this isn't 0.66, it would just be nicer, but it's not. So 0.67, and our millimeter amount that we're allowed is 2.5 millimeters. But remember, we already failed it up here because of this one. We said, well, you're allowed the 2.5, but we got 6 millimeters of error, so that fails. Then we move on to the prism amount that we're allowed, and we're allowed 0.67, but we've got 2.4. Where, you see what I mean? We're significantly away from where we want and need to be. So this pass fail.
Fail.
Correct. So this whole pair would fail with this amount of error because of this amount of power. Okay. These, I think, for the ABO, I know I got a lot of stuff on the thing here now, but for ANSI, for ABO, you need to memorize these, that for vertical, the vertical error can be 1 millimeter, because you only get one eye, it can be off by 1 millimeter, or it can be off by 1/3 of a diopter of prism. And then for horizontal error, PD error, if you will, so this one would be like OC height error. And then for horizontal, you're allowed 2.5 millimeters because we're sharing it between both eyes. And the same for the prism. You're sharing it between both eyes, so you're allowed twice as much, essentially 1/3 in each eye. And this would be PDs. We'll just stick with PD. So these are pretty important to put those into the memory bank. All right, I gotta clean this up for a second real quick.
So what I don't understand is how are we getting the 1.2? How are we getting that number?
Because I started making stuff up. I used the 3 millimeters of error, and I pretended like we had a lens that was 4. So I just quickly calculated them so that we could do the compounding and canceling.
But how do you calculate that? Like what
Prentice rule.
formula? Okay.
Yeah. Anytime you're ever asked about prism, Prentice rule. Okay. Prentice rule. And again, that meridian. So Prentice rule and oblique meridian go together like peas and carrots. Okay. So Prentice rule and oblique meridian to figure out, because oblique meridian is the one that figures out that power at a given meridian.
I wanted to say something real quick.
Go ahead.
Hear me? Okay.
Yep.
With Prentice rule, though, because I was doing corrections for one of Janet's worksheets last night.
Yeah.
And I was so upset because I couldn't get it right. And it involved Prentice rule, but you can change it depends on what the question is, where you can change where things are in Prentice rule, right? Because I kept getting
Yes.
the wrong answer.
Yeah, let me, yes, because that's on there.
See, you do have to, it really, because I know with her question that she was just saying, like, Janet posts videos and stuff, but she doesn't like, not her, but I'm saying that, like, if it's not drawn out, like, if you're not getting the right answer, sometimes you have to change where things are in Prentice rule, or you'll get the wrong answer. I
Yes.
basically still have to figure that out because I spent like an hour yesterday and then I had to go to work and I was like, oh, why can't I get this answer? But then I went home last night and I moved one of the variables in the equation and then I got the right answer. So that formula switches around depending on your question.
Yes, ma'am. And that, I'm glad you brought that up, because that is another one that you're used to doing this format of it, where you like, oh, okay, I plug in my millimeter error here and I plug in my power at whatever meridian here, and then boom, I get my prism, right? Well, some questions are not going to give you, they might give you the prism. And in that case, then you have the prism, and they might give you one of the other variables. So it's always going to be P times 10 on the top. And then the bottom will be whatever you have will give you what you want. Same thing here, P times 10 divided by whatever I have will give me what I want. These two variables can just be swapped back and forth. So it seems like you've got to memorize 3 different formulas. If you're not super, strong on moving these variables over, and I always got kind of weird when we did that. I can do the A and the B, plus and minus and moving stuff around that way. But
so that 10, like,
yep,
on the top one, you have the 10. On the second one you wrote, you just moved where the 10 was.
pretty
Right.
much. Well, I moved the P over too. Because basically you have to multiply. I don't know. I'm not a math genius
Okay,
either.
the 10 is always there. It's just the other variables and where you move the 10.
Yep. Well, yeah, it is always going to be P times 10 is going to be at the top. And then it'll always be divided by whatever you have will give you what you want. Same thing here. P times 10 divided by little d will give me the dioptric power. And an example of this would be, I have a prism amount of 1.5 diopters of prism, and I have a lens power of, let's say, an RX of minus 1 at axis 90. So in this case, what I would be asking you to solve for is what is, how far are we away from where we should be? Okay, so let's say that somebody experiences 1.5 base out prism in this lens. How far are we away from where we should be? So we want to be solving for little d, because we've got prism, we've got dioptric power. The only thing that we're missing is that little d. So it's base out prism. So what meridian do we need to be on? 90 or 180?
180.
180, exactly. So the power at 180 of this particular lens, 90 is the -1. So we're going to add both of those together. So our 180 power is -2. So now I have my prism amount and I have my dioptric amount. And we'll use this formula to solve for little d, right? So remember, it's always going to be prism times 10 divided by the dioptric power, that's what I have, is going to give me that what I want. So 1.5 times 10 divided by 2. Is that right? Yes. Be careful. Because when if you're so used to doing this, you're going to naturally be like, oh, because I just did Prentice rule, I'm solving for Prism. But you're not. We're looking for the little d. That's what we were solving for. So this is millimeters.
Yeah, that's the one that I didn't know last night. Kept doing it, or yesterday, kept doing it a different way. And then when I went home, I was like, what if I move these variables around?
Mm-hmm.
Was able to get the right answer.
Yep. And those are common. I found it common enough on the exams that I just memorized these two, that it's always P times 10 divided by what I have will give me what I want. So you just start looking at your variables and pick, what do I have? What am I given? Oh, I've got my power. Okay, good. I've got a prism amount. Well, I can figure out what that millimeter error is now, or how far the person looked, or um, um, or how much decentration it should have, that kind of thing, just by using the different variables. You hardly ever necessarily need to do this one where they give you like a prism amount and you're told that you have I don't know, a 3 diopter lens. So we have a 2 and a 3. Then from here, because we've got our prism and we've got our dioptric power, well, no, let's say 3 millimeters. A lens was moved 3 millimeters. Okay, this is how this one a lens moved 3 millimeters causes 2 diopters of prism. What's the power of the lens? So you have the prism, you have the little d. We don't know what the power of the lens is. So we just plug and chug. P times 10, so 2 times 10 divided by, what do I have? I have 3 millimeters, so I can solve for my power. So we say 2 times 10 divided by 3 gives us, ooh, we'll round that up. But this is the dioptric power. So don't look at it and say, oh, it's 6.67 millimeters or 6.67 prism diopters, because that's not what we were solving for. We were solving for the dioptric power. Does that make that a more clear?
Yes.
Okay. Yeah, that's a good one to, yeah.
I mean, everybody may have already known, but I just wanted to say it because I had not realized before that you sometimes have to switch the variables around.
Well, and for a long time, I think you're probably not alone. I think for a long time, we really hammer this guy in there. The regular Prentice rule where you're solving for prism amount. But yeah, these are the other uh, options that you have for moving that variable around. Now, and if you're good with you're a math person, you can just switch those around and fine. But I always just remembered it's always going to be P times 10 up top, divided by whatever I have is going to give me what I want. Same thing here. P times 10 divided by what I have will give me what I want. And then it's just a matter of, well, what were you given? This one, yeah, remember this one was we had the prism amount and then we were given the power. So then here we would solve for little d. And here we were given the prism and the millimeter amount. So what's missing? The power. And then we just move those around to figure out which one we need and what. The way that this one usually ends up being used is in this one. And we haven't gotten into it a little bit. Prism for like to decenter the lens to create prism. All right, so you might want to say, oh, okay, well, this, let's say this prescription right here, you know, we've got a -1, and we're like, yo, I've got that in stock. We can cut that today for you. And they're all like, yay, thank you. That's great. I was going to go to the mall, or who goes to the mall, right? But yeah, they were going to go do something. I was going on vacation. Can you make this today? And you're like, yeah, I can make that today because this is their RX. But then you look down and you notice that they had 3 diopters of prism. Let's go base in. I think we've been doing base up. They got 3 diopters of prism base in. And you're like, oh, okay, well, let me see what I can do. Let's see if I can induce 3 diopters of prism in this lens here. Okay, and maybe it will still make cutout. So in this case, you're given what? You've got the dioptric power and you're given the prism. So what am I asking you to solve for? Little d, right? Because I want to know how much do we have to move that lens in order to create 3 diopters of base in prism. Okay, we're at base in, so I want to know what my power is at 180, which we found out was -2. And so then I would need to use this formula right there to figure that one out. So I would say, okay, I need 3 diopters of prism. I need 3 diopters of base in prism, P times 10 divided by, and I have a 2 diopter lens. And I'm just keeping these numbers as real as possible, or, you know, so that you know where they go and where they came from. All right, so then I have, okay, 3 times 10 divided by 2 gives 15 millimeters. Okay. All right, 15 millimeters is how far I would need to move this lens to create 3 diopters of prism. So let's I'm gonna sketch that out real quick. Okay, so here's our lens in minus and base in, right? So we're drawing this on the 180. Here's our OC. If they didn't have this prescribed prism here, then they'd be looking straight through here, right? And in this lens, they'd be looking straight through here. They don't experience any prism at the OC, but we need them to experience 3 diopters of base in prism. Okay, so here's the OC. Let's put it, you gotta have an eye, right? Or are we dealing with the right or the left eye? So here's our nose. Okay, so if we need this person to have 3 diopters of base in prism, which part of the lens do they need to be looking through? This side or this side? A or B? If we need them to be looking through 3 diopters of base in prism.
A.
Correct. So we need them to be looking through here at a point that equals 3 diopters of base in prism. Well, how far is the OC from this point right here where we need them to be looking? 15 millimeters. So basically, we could use this lens that has its OC at the center if we're able to move over 15 millimeters on that lens and have them looking through the point on there, because this is what it would end up looking like. Here's their minus lens. We need them to be looking through here. Okay. So regardless, that's 15 millimeters. So regardless, when we spot this lens in the lens meter, that major reference point needs to be 15 millimeters away from center so that they are experiencing 3 diopters of base-end prism. And this point right here, this major reference point, is the point that needs to go and be placed directly in front of the eye so that they are experiencing that 3 diopters of base-end prism. And so that's just an example of how you might really use this lens, this in practice, to switch this formula around so that you can figure out how much you would need to additionally decenter the lens. Because if you think about minimum blank size, I know these all just connect together. But if you think about minimum blank size, this 15 millimeters of movement away needs to be added into our decentration. So if we had I don't know, an ED of 50, let's just say 50 is our ED, plus 2 times 15 millimeters plus 2. And that's just to get us to the eye. So you can see 30 here. So 50 plus 30 plus 2. And we need a, what, 82 millimeter blank size? And remember, they don't make them that big. So are we making this pair for them in an hour, or do we need to order it surfaced? We need to order it surfaced because this is not going to make cutout because of how far we need to move in order for them to be looking through that 3 diopters of prism that is prescribed. If they didn't have this, no problem. Then they need to be looking through the OC. Their eye needs to be right here. But because they have prescribed prism, we actually want them to be looking through a point that is not at the OC. I just want to take a moment and everybody look at this incredible shot that we got here of Greg's place. Is everybody seeing that? Oh, Greg, come on. Look at that. Well, we had a good shot. You didn't see. We had like some prism and some dispersion and all that. Wow, that's really hardcore. All right. Okay.
I had a question.
Yes.
When we come in next Tuesday to take your final, are you giving us all these formulas? Or no, we just know them. We have to know them.
You need to know them. You need to know how to do the oblique meridian. You need to be able to know how to do Prentice rule. Yes, 100%.
I do know how to do oblique meridian, like off the top of my head, but we need to know how to do Prentice rule off the top of our head. Okay.
Yeah. Because when it comes to the ABO, I mean, and they're going to want you to be able to do that as well, too. And the same with decentration. So the decentration and minimum blank size formula. Be
able to know how to do Prentice rule by just looking at your problem, oblique meridian, flat transposing, any other math formula or no?
Optical crosses, definitely. Know how to do your optical crosses. That's going to be in both of the classes. The good thing is a lot of this does in both classes apply. Prentice rule, oblique meridian, decentration, minimum blank size. There might be some of those with the index of refraction versus the speed of light. Let's see.
I was just trying to like hunt to see like what other math formulas I need to memorize.
Yeah, the transposition. Yeah, the other one is slab off. Are y'all feeling okay about slab offs? Because that, again, that's still oblique meridian and Prentice rule, and you're doing compounding and canceling. But slab off is the ones that you're going to get exposed to here and in the ABO are all going to be vertical. So just like the ones you've been learning, you remember the terms anisometropia and animetropia, those? So that was where you have a difference in prescription between one eye and the other. So let's say we have one eye with a -2, -1 at 45, and we have another eye with a -6, -1 at axis 150. All right, and then we have a reading depth of 10 millimeters. Could be anything, could be 8, could be whatever. And then we say, okay, we'll find out what the vertical imbalance is at reading and determine and fix with a slab off. Fix with slab off. What kind of prism does slab off create in the near? Yep, slab off creates face up, right? So slab off creates base up. So, okay, so we're going to need that in a little bit. But let's figure out what the vertical imbalance is in the reading. So we're doing vertical imbalance. So what power do we need to be dealing with? Power of what meridian? Yep, at 90. All right, so you could do the oblique meridian for this, or you could use that little cheat sheet rule. Remember that 45 degrees is 50% of the sill, right? 45 degrees is 50% of the sill. So 50% of the sill is -50. Add that into the -2, and we come up with a -250 at 90. And then 150 is how far away from 90? 150 is 60 degrees away from 90, and 60 degrees away from 90. 60 degrees is 75% of the sill. So 75% of that -1 is -75. So -675. So these are the two powers that I'm now working with here at 90. And then we're going to take and plug it into Prentice rule. So that first part was finding that the meridian. And now we're ready for Prentice rule. So we are solving for how much prism, because we want to know how much vertical imbalance. So we are solving for prism. So prism little d times big D divided by 10. So we do this for each eye. So how far is little d? Remember, little d is the reading depth. That's how far away from the OC they're going to be looking. So we've got 10 millimeters of reading depth times the 250 power lens divided by 10. One thing I want to point out is take the shortcut. If you're ever given a reading depth of 10, once you figure this out, that's your prism amounts right there. And it's because we can just, those two kind of cancel each other. And if you do it in your calculator, you will come up with 2.5. But it's the same thing with this one times that power of that lens divided by 10 is going to be 6.75. You do it in your calculator, you will come up with the same thing, but whenever you're given a 10, once you get to this point, powers here, you can those are your prism amounts. Okay, so now that we've got our prism calculated, we need to figure out what our base direction is. So we draw our lenses. And we're in the 90, and we have minus powered lenses. So we draw them vertically. Boom, boom, right? Where's our OCs? Our OCs are right here. And our person is reading, and they're looking down, or are reading depth. So they're looking down. And so that person is going to experience what kind of prism in each eye?
Face down.
So we got base down and base down. These are canceling effects, correct? Because the eyes they have different amounts of prism going on, but they are being sent in the same direction. So if this is canceling, we're going to subtract, right? So we're going to take 675 and subtract the less amount from that one. So we got 675 minus the 250. And we come up with 4.25 diopters of an imbalance. And it would be, this was based down and this one was based down. And so this excess amount, or the vertical imbalance, if you will, is based down. And which eye is it associated with? Which eye has too much base down? And remember, this one's the OD and the OS, and I switched them here. So that's the OD and the OS. So this one, right? That one, that 6.75 is bigger. It has more base down than the 2.5. So we would say that this imbalance, we have an OS with 4.25 base down more than the other. All right, so then that is the vertical imbalance amount. So that's our vertical imbalance. We've got our prism amounts, but now we want to correct this with a slab off. So if we're going to slab it off, remember, slab off creates base up prism. Which one of these lenses needs more base up prism to make it match the other one? The base up prism, in effect, the base up prism is canceling, is going to help kind of cancel or reduce excessive base down prism.
OS, right?
Correct. Very good. Yes. So the OS has too much base down prism. Slab off creates base up. So we could just put in, and remember with prism, with slab offs, you can only do wholes and halves. So our option would be either a 4 diopter slab off, or we could go with a 4.5 diopter slab off. That's kind of how they go. Or we could go with a 3.5 slab. They go in wholes and halves. So we got 425, and you always want to round these down because we never want to overcorrect these. We just want to get them to a place where they're close enough to the other one. So that's why we would choose a 4 diopter slab off in the OS. And effectively what that's doing is in this eye, in the OD versus the OS, remember we've got, we ended up with 2.5 base down here, and we ended up with 6.75 base down here. But if we use a slab off and it's going to create base up prism, then of course we're going to use it in the one that has too much base down. And we only need to correct the difference between these. So we figure when we subtract the two from each other, we come up with that 425 base down in the OS that was excessive, if you will. And it was base down. So if the slab off creates base up, then we would use it in the OS. So we would slab off base up 4 diopters in the OS. On the ABO, you need to know how to do this, of course, for these classes, but on the ABO, they are, luckily, they are going to end up doing this for you. You're not going to have that. And then you're going to have your reading depth. There'll be some more info in there, but you know, they're going to try to make it relatively straightforward for you. So when you look at this question, and I know we're about to run over time, and I am going to let you guys go here soon so y'all can take a break between classes. But if you just look at this one, because of that whole 10-10 thing that I was saying, when you look at this one, you don't have to do any fancy calculations. You can just say, well, it was 10 millimeters. Because if I put that in Prentice rule, it would have been 2 times 10 divided by 10. And remember, those cancel out, so we'd end up with 2 diopters of prism anyway. So you could just go right to that. Oh, well, that whatever the power of the lens is going to be the prismatic effect of the lens. It's just a shortcut. Now, once this changes, if this is 8, then no, that doesn't work. Then you have to do it. 2 times 8 divided by 10, and we end up with 1.6. But I did want to just show you that if it is 10, and you will get a lot that do have 10, that it's a little shortcut. If you don't trust it, then you can just work the calculations out too. That you won't go wrong either way, but it's a time saver. Just whenever you see 10 for reading depth, be happy. All right, y'all. It's 11:49. I kept you over 5 minutes. I apologize. But
We forgive you.
If you well, I like to be respectful of y'all's time too. If anybody wants to jump off and take a break, let's do that. We do have another class for lab. Do you guys want to do that, or you just want to not?
Yeah, you're reviewing it for lab, right?
Yeah.
Yeah.
Okay. All right. Yeah, so let's jump off. Let's take a break. Let me turn this recording off. Yeah, let's take a break, and then we'll meet back on the other one at about 12:30. That should give everybody a little bit of time to stretch your legs or think of something else that you might want to ask.